When people first started looking at the sky, they imagined that all those little lights out there were hanging on the inside of a big kind of bowl. Well, not so much a bowl, really, but a sphere that surrounded the Earth. Now, we call that imaginary sphere the celestial sphere. See, here's what it looks like. On the inside is the Earth, and surrounding that is the celestial sphere with the stars on the surface. Now, we know that all the stars and planets and everything are different distances from us, but the idea of the celestial sphere is still convenient for pinpointing things in the sky.
To use the celestial sphere, we're going to pretend that everything in the sky is attached to the inside of this big imaginary sky ball that encloses the Earth, even though we know everything isn't attached to it. If we imagine that all the stars and stuff are attached to the celestial sphere, it's easier to visualize their position in the sky when we're looking up at it from the Earth.
Here are the terms you'll need in order to understand locations on the celestial sphere.
The celestial sphere has poles in the same places as the Earth. Imagine that we set up big searchlights on the north and south poles of the Earth. The north and south poles of the celestial sphere are where the searchlights hit the celestial sphere. See how they're lined up with the Earth's poles.
In between the celestial poles, right on the surface of the celestial sphere, we draw an equator just like the Earth's equator.
Now imagine that we draw a line from one pole of the celestial sphere to the other. It goes from the north celestial pole through the middle of the Earth and right down through to the south celestial pole.
The line between the north and south poles of the Earth is the axis the Earth revolves around. When we look at the stars on the celestial sphere over a period of hours, they seem to revolve around this axis.
So, here's the Earth, and here's the celestial sphere around it. The Earth's north and south poles are here and here. Remembering our searchlights, celestial north and south poles are here and here. Here are the equators. Now, if you're standing here, there are a couple more terms we can use. The point on the celestial sphere that is exactly above your head is called your zenith. The exact opposite point, the one underneath your feet all the way through the Earth and on the other side of the celestial sphere, is called the nadir. No matter where you are on the Earth, the point above you is the zenith, and the point below you is the nadir.
Now, imagine that we draw a great circle on the celestial sphere from one pole to the other through the zenith of our position. This line is called our meridian.
Part 2. The History of Astronomy.
Section A. The beginnings of astronomy.
In the West, the science of astronomy really began with the Greeks. Around 600 BC, guys like Thales and Democritus wondered what made up the world and how far away the stars were. Other people probably thought about it before them, but these smart guys were the first to write it down.
Later, Pythagoras showed up and started thinking about astronomy stuff. He and his followers believed several things, including that the Earth is round.
They decided the Earth is round because the phases of the moon seemed to imply the moon is round. To them, the moon looked like a spherical object that had light shining on it from different angles, which it pretty much is.
Unfortunately, some of the Pythagoreans also believed that the Earth was the center of everything. We call that idea a geocentric universe. Remember, geocentric universe, Earth, center of everything.
I'm the coolest person on Earth. Everything revolves around me. I am geocentric.
No, girlfriend, that's egocentric.
Actually, some of the Pythagoreans believed that the Earth moved in small circles near the center of the universe. This is really splitting hairs, though. They essentially believed that the Earth was the center of everything.
The Pythagoreans also believed that everything in the sky was fixed on big celestial spheres. The celestial spheres for the Pythagoreans were different than the ones we use now. For the Pythagoreans, the celestial spheres were big glassy circles that actually held the stars and planets in the sky. They said that there was one celestial sphere for all the stars, one celestial sphere for each planet, and the sun and moon had their own celestial sphere too. The Pythagoreans believed that if you listened really closely, you could hear the spheres rubbing together. Silly Greeks.
The next big dude in Greek philosophy was Plato. Plato thought about a lot of stuff and was very influential, so his thought on science and astronomy stuck around for a while. Plato thought everything in the world was made up of a mix of 4 elements: earth, air, fire, and water. Everything but the heavens, that is. The stars and planets were made of a godly stuff called quintessence. Since they were made of God stuff, Plato reasoned, the planets and stars must move in God paths. What shape are God paths? Circles.
Plato reasoned that the planets and the sun and the stars moved in circular paths around the Earth. Circular paths seemed to make sense to everyone, and the idea that objects make circles in their movement dominated for quite a while.
Aristotle was Plato's student and probably the most influential person in ancient astronomy. People followed Aristotle's ideas well into the Renaissance.
Aristotle believed that astronomical objects moved in circular paths and that the Earth was round. Aristotle figured the Earth was round because during a lunar eclipse, the Earth cast a round shadow on the moon. Pretty clever, huh?
But Aristotle also believed the Earth was the center of the universe. Aristotle rejected the Pythagorean idea that the Earth moved. Aristotle said the Earth was immobile and the heavens revolved around it.
Aristotle said the Earth was the center of the universe, and everyone believed him. After a while, the Catholic Church even decided that it was a sin to believe otherwise.
After Aristotle, people continued to believe that things moved in circles. Ptolemy tried to incorporate the idea of a geocentric universe with the planets moving in circular paths around the Earth.
Ptolemy's model was really complicated and looked something like this. The planets made their orbits around the Earth, but as they did, they also moved in small circles along their orbits. This model tried to explain the movement of all the planets, including retrograde motion.
Retrograde motion is something that happens to planets. If we look at where a planet is in the sky every night, it tracks a slow, steady line across the sky. But sometimes, when we're looking at a planet that is farther away from the sun than we are, its position in the sky seems to jump backwards. This is retrograde motion.
Retrograde motion happens because we're moving at different rates than the other planets. Sometimes the planets can seem to move backwards in the sky. This happens because the Earth is moving faster than they are, kind of lapping them.
Imagine you're in a car going around the inside lane of a racetrack. Every 5 seconds, you look up to see where the car in the outside lane is. The first time you look, the car is ahead of you. The next time you look, the outside car is going around the turn, so it seems to have moved ahead to the left. But now, the next time you look, you've gone into the turn too, and since you're on the inside lane, you make the turn faster and you catch up to the outside car. When you look out the window, the outside car is right next to you. If you didn't know any better, you'd think the outside car moved backward. That's how retrograde motion works. It's when something seems to move backward because you're catching up to it and moving past it.
Some other Greek astronomers made important and accurate discoveries.
Aristarchus believed in a heliocentric universe, meaning that the sun was the center of the universe. Of course, he couldn't prove it.
Eratosthenes, using trigonometry and careful observation, measured the circumference of the Earth within 1% of its actual size.
Hipparchus discovered something called the precession of the equinoxes. This refers to the fact that the Earth wobbles like a top as it revolves. The wobble makes the North Pole point at different places. The wobble is really slow, however. The North Pole makes a full revolution and points back at the same spot every 26,000 years.
The wobble of the Earth causes the identity of the North Star to change. The North Star is the star that the North Pole is pointing at. Right now, the North Pole points pretty close to Polaris, which is our North Star. The ancient Egyptians had a different North Star because the pole was pointing at a different place. The Egyptians' North Star was Thuban.
When the Roman Empire fell, Europe went into the Dark Ages. People in Europe were too busy warring on each other and getting the plague to do any science. The rest of the world kept working on astronomy.
Whoa! Arabian astronomers in particular provided a vital link between ancient and modern astronomy. Many of the trigonomic formulas, and even the names of the stars, come from the work of medieval Arabian astronomers. Renaissance scholars used the work of Arabian astronomers when they began working on astronomy again in the 1500s and 1600s.
Section B. The Copernican Revolution.
In 1250 AD, the King of Spain decided he wanted to know where all the stars and planets were in the sky, and where they would show up in the sky every year. So he commissioned a group of astronomers to compile a star almanac. The Spanish astronomers used Ptolemy's model of the universe to compile their observations and make their predictions. Ptolemy's model was that really complicated one that used planets rotating in smaller circles on bigger circles. There it is, that's the one. Okay, back to the Spanish astronomers. Their star almanac failed to predict anything about the sky with any accuracy whatsoever, except, of course, that the sky would be dark during the night.
Ptolemy's model was horribly complicated, and it hardly worked. And it contradicted one of the most famous philosophies of the time, Occam's razor. Kind of a weird name for a philosophy, but that's what they called it. Occam's razor stated that the best theory is the simplest one. It makes sense, doesn't it?
So, Ptolemy's model was really complicated, and it directly contradicted Occam's razor. Everybody knew that, but they tried to ignore it because no one had any better ideas.
The Earth is like a great hunk of mutton with onions and potatoes and very small green things that taste faintly of curry, but... Lunch break!
In 1473, Nicholas Copernicus, a clergyman in a Roman Catholic cathedral, wrote a brief statement. Essentially it said, "We live in a heliocentric solar system. The sun is the center of everything. We live in a heliocentric solar system. The sun is the center of everything." Now, if you remember, the Catholic Church said the Earth was the center of the universe.
Despite this, the Church didn't seem to care that Copernicus was announcing his belief in a heliocentric solar system. Mostly it was because his statement was poorly written and not many people paid attention to it. Besides, Copernicus was working on calendar reform, which the Church really wanted done, so they figured they'd leave him alone until he was done with the calendar.
So Copernicus wrote some more. He made a whole book. In the book, he continued to argue that the Earth revolved around the sun. God would surely find a simple heliocentric universe more pleasing than the complex Ptolemaic model he wrote. Besides, Copernicus argued, the Pythagorean model with all the rotating celestial spheres wasn't logical either. What makes more sense, that the Earth revolves around the sun, or that giant celestial spheres rotate around the Earth at astronomical speeds without breaking apart?
Enemies of Copernicus criticized his book. He didn't solve the parallax mystery. He couldn't explain why the Earth orbits the sun, and his model couldn't provide accurate data. And the Church argued that the celestial spheres couldn't break apart, because the quintessence they were made of weighed nothing, and could therefore spin as fast as necessary.
Copernicus didn't get much credit while he was alive, but his idea was starting to catch on.